Is there work done by anything other than gravity? There's no friction. No. So there's no work done. Okay.
Normal force that causes it to change direction is going to be perpendicular to its direction.
Yeah, and once you get into the curved path, once you get down there on that curved path portion, then that thing is, then that thing only has transverse force exerted by the wire against it, and that does no work because there's no displacement in that transverse direction. Okay. So the condition we have in this particular problem here's the governing equation, is that there's no spring, so there's no change in elastic energy. And I would encourage you to write the governing equation down and then zero things out appropriately. And if you say over here on the side, no spring, that's not a bad thing to comment on. Oh, and regarding the homework that I reviewed, most of you are doing very nice work, and it looks really good. The only criticism I would have for most people is put more English in there. Most of you are hot shots with the math, but the explanation as far as what you're doing isn't there. So just try to force yourselves to include some English comments. Okay. In some cases, additional sketches. In some cases, showing a little more detail in your work. And in some cases, writing a little larger. Okay. And in a few cases, you need to put more time into this subject so that you can really master it. Okay. But most people seem to be working pretty hard at it. There's no friction, as we said. There were no other active forces, no cables hooked onto it or any of that. So this term over here is zero. This stuff on the right side, we just for simplicity, we call it DeltaE. It's the change in the energy in the system. That happens to be equal to zero. If the change in the system that embodies gravitational elastic potential change is equal to zero, like this, then this is called the principle of conservation of dynamical energy.
Okay, so all U is force, is all U represents is energy that's been put into the system through something, cables pulling, whatever happened.
Anything other than, this U over here, anything other than gravitational effects or spring, elastic potential effects. Yep. So this is conservation of dynamical energy is what we have. So you can kind of look at a problem and decide if it meets this criteria. And then if it's true, then that means, look at what we have going on here. Delta T plus delta VG equals 0. It means there has to be a little balancing act going on here, which I've already talked about. If one of these increases, the other has to decrease, or vice versa, in such a way that the sum is 0. Okay, so we have a picture for this problem. The object was originally up here at A, comes down, whips around a circular arc, and then comes back up to 45 degrees above that level. And what was the radius?
0.15 meters.
0.15 meters? Okay.
And it drops 0.6 meters from the top of A to the level of the radius.
0.6 meters. Okay, 0.6 meter drop right down to here. Good, very nice. And here's location B. So I'll tell you what, just this is a really elementary problem. Let's just do it start to finish and not try to embellish it with a bunch of generalized equations for variable angle theta. We can do that on another problem, okay? Because I'd like to do something where we've got a spring, some spring elastic energy going on too. Everybody good with the problem? Okay, why don't we set the datum It's arbitrary, isn't it? That's our choice. We could set it here at this level. We could set the datum up here at the starting level. We could set the datum at the very bottom. I think to reinforce the comments I made earlier, I want us to set it at the very bottom. Then, what we can do then is we can easily measure, and I'd like you to make sure that you write that down where you're placing your datum. It makes it easier to look at the mathematics and see, rather than me having to look into the mathematics to decide where you placed your datum. So just write it on your sketch. Then what's going to be nice about this is by placing the datum down there, look at this. This location was H1. This final location is above the datum also at some H2. Actually, I'm going to call it HB and HA. That'll make it easier for us. Feeling good? So here we go. Change in kinetic energy. 1/2 the mass was
0.25 kilograms.
0.25 kilograms. And then we're going to have VB squared minus VA squared. But the thing started, I believe, at rest. VA was equal to 0, so that zeroes out this term. And then we're going to add to it the change in gravitational potential, which is the mg 0.25 times 9.81 times H final, reference from the datum, HB, minus H initial, reference from the datum. And that sum has to equal 0. So this is 1/4, and half of 1/4 is 1/8. And then we're going to kick those terms. Actually, it looks like the 1/4 disappears, doesn't it? Divides out. So why don't we just divide that out? It makes life a little simpler for us. And then we're going to just kick the 2 over after we've moved these, the potential, gravitational potential to the other side. And see what we get. Oh, what kind of a value are we going to get on the gravitational potential? You know what I think I want to do is do the math here so you can see the value, the actual numbers. So HB is going to be the radius plus 0.15 sine of 45, right? So I want to go ahead and show you the values we get out of this. 0.15, and if I factor that out, because I'm adding to it, it's 1 plus the sine of 45, which is square root of 2 over 2. Oh, and then that's HB minus HA. HA was 0.6 plus 0.15, or 0.75. This is 0.707. Did I do this right? Something's, the numbers.
Yeah, I don't think you.
The numbers are looking.
0.15 should not be multiplied by the 0.75.
And that needs to blow itself a little deeper.
Oh, that's what the issue was. Thank you. Thank you for catching that. What I wanted to make sure was clear. There we go. That's better.
There we go.
Yeah. Now, why do you think I was aware something wasn't right there? Why do you think I was aware something was wrong?
It was going to come out to be positive.
Yeah, the result there would have been positive. And what do we know? If the object was here, what kind of change in gravitational potential have we seen?
It loses
A
gravitational.
loss in gravitational potential, which means it started here with zero velocity. If it's given up some gravitational potential, when it gets to here, it's going to have some velocity. So we have to see a negative on this expression, and that's what I wanted to make sure I showed you, and I almost screwed it up. So this number right here in front is going to be less than 0.75, so you're going to get a net negative result out of that. Okay. And then here we have our half of our square of the velocity. Might as well, for completeness, include that. 0.5 with a VB squared right there. And then if we kick that term over to the other side, that then becomes positive, a result there. And we multiply by 2 and take the square root, and we'll get the VB out of that, which, that would be the speed it's carrying. And I didn't write that down. Anybody punch that up?
Yeah, 3.11 meters per second.
Okay, 3.11 meters per second. Now, that's not what the question asked. The question asked us to find what?
Normal force.
The normal force. So at B. So what we need to do is draw a picture at B mg, no friction, and so the wire, I'm going to go ahead, and this is arbitrary, I just have to make sure I place it in the proper direction, transverse to the curve, and then I need to define some unit vectors on here to be able, because we're trying to figure out what this normal force is at this location B. So what I think I'll do is I think I'm going to go ahead and use normal tangential. On there. And then let's go ahead and write the equation for the sum of forces in the normal direction. See if we can figure it out. So if we write sum of forces in the normal direction must equal the mass times the normal acceleration. And we know that normal acceleration has to be the speed it's carrying at B squared divided by the radius it happens to have on that arc. And that's got to be equal to the sum of normal forces, which means it has a positive capital N. And we have a component of mg that's also in here at 45 degrees, so it's going to be plus mg cosine 45. Any questions so far?
Does that say VB squared?
Excuse me?
Is that VB or it's VB, right?
Yeah, the velocity at B. We're at location B.
Yeah, M times VB. It just looked like an R. I got confused.
Oh.
I'm good. Thanks.
There we go. So now we can solve for n because we know what VB happens to be. So we're going to get the normal force then is going to be our mass, which I could factor out. And we're left with VB squared over R minus G cos 45 square root of 2 over 2. and we can place our numbers in there. Our mass again was 1/4 kilogram. Our speed, 3.11 squared over the radius, 0.15. And we're subtracting from it 9.81 times 0.707 for the normal force. That result should agree with what I wrote in the book.
Yep, 14.4.
14.42. Newtons. .42 newtons. What you're going to see in a lot of quite a few problems is when you're doing the energy, your kinetic energy terms, and you're finding velocities, I would suggest you write down what the square of your velocity value is, because you're going to see that show up frequently in cases like we see here, because you're looking for that normal acceleration, which involves that square of the velocity. So just jotting that down, that value down, will save you having to do an extra calculation. Okay? So that's how you do these, and I think we should work probably another problem or two and make sure we do something that's got some spring type of effects in it. Here's one that's, unfortunately, it does not have any friction in it, and I may or may not have time to get to one with some friction today. So let's take a look at this one. We have a 10 kilogram collar, slides on a smooth vertical rod with a velocity of 2 meters per second as it passes this horizontal position up here. Oh, and check this out. The spring, each spring already has, right here the springs are 0.4 meters long. Each spring, as it passes through this position, already has some stretch in it of 1/10 of a meter. So there's already some stored energy in the spring, right at that spot, the way this thing was set up, this 10 kilogram mass. And it's got some downward velocity. So the question is, calculate the velocity of the collar as it passes point B. And point B is 3/10 of a meter below the horizontal position. The springs carry 800 newtons per meter stiffness. Okay, so that's the question.